And if it's an electron charge, which means it's going to break the stability. But if they stay the same polarity, there's no outside force, right? There's no outside force affecting them. So they shouldn't move towards each other. As long as you don't move towards each other, you're good to go. Hey Jennifer, how you doing? Can you hear me?
Yep, I can hear you.
All right, perfect. How's everything?
Going all right. I was going through some of the questions for this chapter.
Okay. Yeah, like it's I did take a look at. Thanks for sending that to me. Yeah, usually like the way I do it is like, do you see my screen by chance?
Yeah, I do.
Okay. Yeah, I have checked, but like I kind of don't like. There's a lot of like wordings in check. I usually just like do my own solutions. But like
Okay.
for this one, maybe like because it'll definitely help if you have like a step by step concise solution.
Yeah.
Um, And then typically the way I would like show this is on OneNote, like on my iPad, but I didn't have time today. But we can definitely do that on the next ones. So for your homework problems, I remember you were like, I guess before we talk about this, you mentioned something about like Gauss's law as well.
Yeah, so that's the next chapter. I just finished watching the lectures for that. He posts them ahead of time. And so, yeah, Gauss's law and then Gauss's law and conducting or conductors or something.
Chapters, yeah. Okay. That one I think is the other chapter after. Usually, like the way I learned like physics two. Usually, this is like you go with like charges, and then you learn the Coulomb's law, right?
Mm-hmm.
And like the electric field, and then Gauss's law, and probably like conductors and then insulators later on. We'll talk about those later on.
Okay.
But you just to get like the background, your exam upcoming is on Friday.
It's actually I moved it to. It was supposed to be tomorrow, but I just felt like I wasn't prepared, and so I moved it to next Thursday.
Oh, perfect. Oh, like, so you just asked the professor, pretty much.
Yeah.
That's,
Yeah. I've
okay.
been behind a little bit. And so yeah, he said I could do it next week and put me even more behind, but I'm like, I'd rather be more prepared and not fail the test than
Yeah, exactly. That's good. I'm glad that you did that. Yeah, I was gonna say like, yeah, it's not that big of a, like learning all this, all like maybe in 2 days, but like the more time you have is always good.
yeah.
So,
And
like, yeah,
that's kind
yeah.
of what I figured.
So maybe we can like like, so how many homework problems? Maybe if you can send me like all your homework problems like after
Yeah.
this.
Yeah, for
Uh,
sure.
yeah, because like I can like give you all if I have because today if these number like 4 problems I can definitely do them and additional problems and now we have more time.
Yeah.
So for the next one I'll show you like my workout solutions, which would be very helpful. A lot of people find that very helpful. Once they find like because the theory, how are you with the theory? Is it easy
Um,
for you?
okay. Not great, but I mean, I understand, the general concepts for point charges and things like that.
Okay. And then the
Here.
equations, yeah, derivation. Okay.
Mhm.
Yeah. Because like what we have here is technically just like applying Coulomb's law, and then the other ones is you have like the forces, right? Like
Mhm.
now you have like Newton's second law along with like Coulomb, and then the electric field, and then you just have to like work out the equations and see like mainly what I usually do is you just have like I would say like what the givens that you have a
Mhm.
lot of times it's hard to like configure what equation that you need to or like what givens you have to apply to the equation
Yeah.
and and figure that equation, it's like, oh, am I still missing a few things? The best way is just, you know, I you probably already know this, but like just lay out all your givens and then find out what the question is asking you.
Okay, yeah. And
And
I try to do that. With this
okay,
one, it's more just a case of it's the insulating rod thing that throws me off because I know that this chapter has some of the integral stuff, and I just
yeah.
really don't understand any of it.
Oh, the integral stuff. Okay.
Yep.
Uh, it if for that, that's kind of like that reminds me of Gauss's law when you do like the integral of E and
Yep.
dA. Yeah, those ones typically like that's why you could actually like a lot of times I say once you have the derived equation
Mm-hmm.
um, like for spherical and then your cylinder and like a lot of it is just using those equations. Do you guys have to derive like did your professor say you have to derive something maybe for the midterm?
Um, he didn't. He did a few derivations. Some of them he just kind of skipped to the end though, which was a little frustrating. But for the most
Uh,
part, he gave us the derivations for the different like cube, cylinder, sphere, stuff
Yeah,
like that.
that's for all like for Gauss's law. Like a lot of it is just, you know, you have a heat flux through like a surface, right? Like,
Mm-hmm.
and then it really depends on what type of shape that you have, and then like
Yeah.
how you. We can probably work out a few of those like later on, not today, but the Gauss's law stuff.
Okay.
Uh, for chapter 24, we definitely can, and then use that to like apply. Uh, how strong are you with like because you say the integral like it's pretty much an integral. How strong are you with your calculus?
Um, Relatively strong. I'd say probably about average. Or
Okay.
maybe slightly above. It's just for me. It's been a long time since I took Keck 2, and so
Okay.
applying it is difficult when it's been that long between.
Yeah, I know what you mean. So yeah, like maybe we can like look at those problems specifically, like
Okay.
actually derive the integral for
Okay. Yeah.
different. Okay, but for this one, I guess for today, let's like try to dive to these, and then maybe you can let me know like what parts you don't know or
Okay.
confused. Okay. So
With
for this one, like this one is not that bad. These are very typical. You see my my pink cursor.
yeah.
So this these two typically this is what how you would apply like the equilibrium in terms of like Coulomb's law because then you have the forces, right? You have these two charges, and because they're charged, they produces a force, and then depending on like this distance between the two charges, point charges, the farther away they are, obviously the lesser, right, the force, and then the greater the charge, which is very deliberate here. This one has like a greater charge because it's bigger, then the greater the force as well.
Okay.
But so like what this is like it does give you the way this check is like showing it in the solution. Like I'll point it out, but is like they were a little confused, and the way they present it is a little bit confusing with the Q2 here,
Okay.
because big Q is this unknown charge, the third bead,
Okay.
and then like when they present this as like the 3Q, and then this one is supposedly just 1Q, and then this is the unknown big Q, and
Yeah.
then in essence, what this is asking is how far is this so that there is no like force. So in equilibrium.
Okay.
And how you do that is just pretty much like you're gonna mess with the Coulomb equation and then Newton's first law when you equate them together. So when you write the expression, this is Coulomb's law, right?
hmm
Yeah. So K is usually a constant. Yeah. I'll just explain every part because it's always good to like be repetitive with it. So like you
hmm
get the concept as well as like the procedure, and then so this K is a concept. It's a constant, and then Q1, Q2. These are what I'm talking about. Like if you have 2 point charges, it's either this guy and then this guy. Usually you apply it like that's this R. I've seen this as like D usually, but it's just a distance between like 2 point charges,
Okay.
and then for this to because we're talking about this unknown bead, the
hmm
charge here, this R will be this X,
Okay.
from Q1 to this unknown, and then Q2 to this unknown guy. So, and then that's why once you equate it, you can figure out what this X is. In the end, it'll be like, okay, that's the only unknown that you have.
Okay.
So, okay. Um, so the first thing is let's apply that to like the first guy. So
So you plug
as
it in
you,
here, yeah.
yeah, you just plug it in. Like so, the Q1. I guess they took this as the unknown,
Oh,
or the yeah. See, like over Q1, Q2. Q1 is the 3Q. Q2 is like the big Q. Yeah. So I wish I
you
could
do
like
that.
draw.
You do that for Q1 and Q2, right? Like the force between both of them. You
Yeah,
do it
like
separately.
it depends on like which one you're like treating as one and two. So this is for them is the Q and the 3Q, and then the unknown big Q.
Okay.
And K and an X squared, that's the distance between them. So you leave it as that, and then you look at the second one now, the second force. So this is between like the small point charge and then the big Q. So, but the thing is here is like you got to be consistent with your notation of like how that's why it's always good to draw a picture.
Mm-hmm.
It's like this big this D that's good is the distance between the Q1 and small Q2.
Okay.
But then you don't want to be using like x1 or x2. You just use like x, and then you in order for you to find like the other x, it'll be like d minus x. So you
Okay,
just
that
have
makes sense.
less variables is good because you're going to be solving for that x. It's like this x right
Okay.
here. So you want that to be just one x. So that's what they did here. Is they did like the difference of the distance.
Okay, and that's
And
the different F2. Okay.
yeah, like, and then so you have the force of one, force of two, and then like okay, you want this, you want to find x at equilibrium, right? So
Yeah.
that must mean that net force is zero. Newton's first law. So
Oh,
at
so you
rest,
set them equal to each other.
yeah, you set it equal to each other.
Okay,
Very
because you want to do easier. Okay.
yeah, and then once you do this, it's like from the wording of the questions, like at what position is the third beat in equilibrium? This equilibrium already tells you like, oh, you're gonna be doing something that's gonna be in zero, equate to zero, or in other words, they must equal each other, right?
Okay. Yeah, it's some of that wording that I think really does throw me off too on these problems.
Yeah. Whereas like a lot of every time I get like a lot of questions on this is like, how do you like translate the words into mathematical terms? And
Yeah.
that's like a skill. Over time you're gonna build that like that intuition into like learning how to like okay different like for example like you could make all these variables different, but then just be consistent. And in the end, like you don't even have to do this. You can make it like this guy minus this guy equals zero. You could solve it that way. It doesn't have
Okay.
to, like there's different ways of doing it. But like, just knowing what you can assume. Like once you know what your assumptions, then your equations kind of like fall out of that.
Okay.
So after you do this, you rearrange, right? Because
Yeah.
this Q here is the
Those
same.
cancel.
Yeah. And then the Q as well, and you're left with like all this, and then it simplifies to this guy. And then which is easy because then you have this D, you just need the X.
Yeah.
And then it just becomes a mathematical, equation, right? A quadratic
Mm-hmm.
equation. And so the result of this quadratic equation usually is 2, because it's x squared, is usually 2, and
Okay.
root. And so these two, you have to assess which one you need or which one is valid, and because this one right here is not possible because it's probably somewhere over here.
Okay. Yeah,
So
because D is 1.5. Yeah.
yeah, it's gonna be the one like up to D or less
Small
than D.
one.
Yeah, like that one, it's not as bad. What do you think?
Yeah, it's not too bad. I think the big things I struggle with are picking up on the words like equilibrium and things like that. Because I
Okay.
know there was another problem that I was struggling with where I just didn't, kind of connect equilibrium as with its mathematical counterpart.
Yep.
Um,
Yeah.
so I
Like
think
a
that's
lot of like there's another one as well. Like so like a lot of problems I would say with like how this usually gets written is when because like Coulomb's law gives you the force, right? Because of the charge.
Mhm.
Like there's a charge between two particles. That's why you get the forces. Every time you get forces, um, someone could always ask you when are they in equilibrium? Because it's a force, right?
Yeah.
Like it's like any other force. Like when you took probably like physics one mechanic, like it's all mechanics. A lot of it like statics when the force is zero. You can apply those exact notion into this, but then now we're using charges inducing forces.
Okay.
But like exact theory is the same.
Okay.
Especially later on when we're gonna talk about this the sliding block. That one I've seen in physics one.
Oh yeah, I have too. I just don't remember how to do it very
Yeah, like
well.
when you do the free body diagram, right?
Yeah.
Like a lot of it is just that, and then that's why it's very interesting. Like I guess electromagnetism, because then it does touch on that. Like like all forces are induced by charges, and then like electrons moving, is it also relates back to like thermodynamics if you're taking that.
Mhm.
And if you have like excitation of a lot of like electrons, that means like things are getting hotter, and then when things are colder, you have like positive charges, something like that.
Okay.
And oh yeah, I gotta explain this one. Do you understand this can the equilibrium be stable question?
No. Mm.
Okay, so when it's asking this, when it is in, it's like a conceptual question in essence. Like when something is in equilibrium, you don't want them to move, right? Like when you displace them, and it and then they don't go back to the same position,
Yeah.
that means it's stable, right?
Yeah.
But like if you displace it and then okay, they go back to the same position, then that means it's stable. And how that can be applied to to particles, protons, electrons. It's it depends on their the sign, like the polarity.
Okay.
So like if these were to like be like this is positive, and if this is like negative,
Then it'll.
then it's gonna cause some displacement somehow. It's not gonna
Yeah.
go back to the sky. It's gonna attract here, attract there, and then so you can keep the equilibrium, but because that's the reason why we were able to get this distance. But
Yeah.
it's gonna change. The way you can like in place that or implement equilibrium there for it to be stable is it has to be the same charge to
Okay.
keep it like at that point.
Okay.
Okay. Yeah, so this is a very like I guess a very typical this a lot of problems of like Coulomb's law involves doing this. Sometimes I've seen this where it's not in line, like it's somewhere down here, the unknown.
Yeah. So, how
Yeah,
would you do that? Use if it's like trig or whatever.
yeah. So for those ones, yeah, all you have to do is figure out this distance, and then maybe you're asked to do like fx and fy.
Okay.
And then you just take like square root of fx squared plus f fy squared, and you get f net, something like that. That
Okay.
maybe that one I'll look for a problem like that's kind of similar to that. I've seen that before. That's why maybe your professor's gonna give you that.
Yeah, he
have you
may.
have you taken an exam for him yet?
No, I haven't, which sucks because I don't really know exactly what to expect.
Yeah, I know. It's like yeah, like the very first one is usually like maybe yeah. This is when people like study so hard, like the very first exams.
Yeah.
Out like, oh, it's or maybe he's too good, or like he gives you a lot of hard problems, or it's just too easy. So we'll figure
Yeah.
that out.
He's definitely more on the hard side, and he said that himself too.
Oh
Um,
no. Okay.
because yeah, no, I mean it a little bit of both. So he said the integrals on the exam won't be bad.
Oh,
But I
so there
mean,
will be integrals. So he did hint that. Okay.
yeah, so there will be integrals. And so I mean that's hard, but he said he won't make them the really complicated ones, which I mean I guess that's relative. So it depends on what he considers to be hard or not.
Yeah.
He
If you
said
study
he
them all, yeah. If you study them
yeah
all, you'll be good. Yeah. We'll see.
yeah. But he said like he will do a point charge question
Okay.
where
That one.
you have no point charges on at the origin, and that's
When you
one I'm not sure how to do.
yeah, I wanted to like kind of like prod that. Like, what do you mean by not in the origin?
Okay, so a lot of the point charge questions, like if you went to 12 before this one,
Let's look at
where you're
12.
just trying to find the magnitude and direction of the electric force,
Okay.
he's saying that he'll give questions where you don't have anything at the origin. Or actually, okay, I guess the better one to look at would be 11 because it's the same thing.
Let me look at that one. Let's see. This
Yep,
guy?
that's it. Yep. So he's saying that like
I
the
see.
5 would be somewhere
Inception.
not at the origin.
I'll take a look at this. I didn't know what you meant by that, but like it's kind of like in my mind, it's looking at this thing, Coulomb's law. You just apply the same concept. It's just there's gonna be an x and y component. Like I said, there's gonna be an x.
Yeah.
And y.
So I can do it when it's like that. My concern is if he takes that 5 and like shifts it up so many meters or like a tenth of a meter or whatever,
Yeah.
how that affects things, because then you have to take that into account. And so I guess that's one of my bigger concerns, because I can do it when it's like this, where you always have points or charges at the origin.
Yeah.
But if you don't have one there.
Okay. Let me look at this when is there another problem where it's not in the origin? This guy.
So in the book, no, they're all in the origin.
Okay.
So this will be a product of his creation.
No worries.
Kind of
I'll try see if I can like make up one and try to like obviously formulate the solution for it.
Okay.
Because it's gonna be very similar to this. It's just maybe it's just a level up from this, right? Like it's this and like obviously harder, and which I don't think isn't that bad. It's applying the same concept as long as you're being consistent with what you're applying here. It's really it's whatever I mentioned, like x and y, and then your signs has to be correct.
Yep.
Yeah, we'll talk about that later. Like maybe like tomorrow or like Friday. We'll see. Once I get to it. So okay, so that was that problem. What about this one?
This one I just throws me because it's an integral. It's one of the integrals.
Oh yeah. Okay, let's talk about like the givens first. So what this is really is just like you're given this like charge, and then you also you need to find the magnitude and then direction. And in direction, this means like if you assume this as positive, then left is like negative, And then setting this the integrand, like that's like one step. You have to set up the integrand before you do the integral of this guy. So that's like the very first thing they do here. So basing this off the electric field equation, you have K still. The other one was Coulomb's law, and then so you have this charge over like the distance squared. So, and then for like a linear charge, this is because there's like what is it? There's the spherical, right, and then there's the cylinder, and then there's a plate. I think this is flat. Yeah. So you can apply this equation. So yeah.
And that's just the equation for when it is flat like that, like a half cylinder that's flat.
Let me read this. Rod of length. As I remember, let me think. I think it was. It may be the cylinder. It may be a cylinder because there's a rod, right?
Yeah.
Yeah, there's a rod. Okay, but it doesn't give you like that diameter. It just gives you like the length. Anyways, when it's like a cylinder, you can assume this because like there's different charges, depending on like what shape you have. So this is, I think, the cylinder one, where you have this linear charge density lambda times the length. So that's given. Like once you know this shape, this guy is what I'm saying.
Okay.
And this one, this equation by theory, and then so now this is where the math part comes in, like the very nitpicky one. So. What you have to do is you have to assume a few things, like where is this d theta, where is this dl. So so when you look at this equation right here, you just take the differential, and then but then the sine theta is like when you're taking like vertical and horizontal components. If you look over here, the horizontal component is the sine theta of E, not the cosine. Okay.
What is physically dE on the rod?
It's the differential, which is like a small portion of like the electric field. Yeah, see if I'm able to draw this out, I'll give you my actual picture of it. But what it is like a small segment of the center. No, a small segment at the center. Also. How like when you have this, it's like from here to here. That's the dE. Like from this point to like some point over here.
Okay.
And then so once that's the take the derivative of that, and then this is E times the sine. You have this guy. This is going to be pointing to the left. And then
that's taking the derivative of what?
Of E. of this guy.
Gotcha.
Yeah. So, because what you need to do is you need to put this in the, you need to take the integral of this. It's like, that's why we're doing this first. You always have to do this first,
Okay.
so that you can actually get the e. So you take the derivative of this, and then
And
you
then plug in the Q.
plug in the q, right? Okay.
Yep.
And then here's another thing. So you have this like L, but everything that's like what is it? A dimensional. So L is like a dimension.
Yeah.
Lambda isn't. You take, since you're taking the differential of like the electric field, you also have to take the differential of the length.
Okay.
Yeah. So, and that's just like, you know, that's like the math concept where you have like dE and then dL. Because this side is taking differential, and one side, this length has to be also a differential. Well, and then once that's set up, then you could take the integral of both sides. So when you take the integral of this guy, you obviously get e. But then where, from what to what? This is a semicircle, so 0 to pi.
Okay.
And then like, so this is the part that it's not that bad. You need to assess first which ones are constants. So k is obviously a constant, lambda constant, this r is a constant, and then you only have this differential, right?
Yeah.
But we don't want to be working with like L if we can, because like if you remember arc length, this is like, okay, why do you use this? You know, like, so when you take a differential of like L, you know, the length of like this rod, since like this is a semicircle, you can actually take you can make that in terms of the r. So it's r and then how far away you are. So that's like theta.
Okay.
So r theta equals like that's like arc length pretty much, which is this guy.
Okay.
Okay. So you plug that in here, and then so your equation becomes this guy. And now this r is not really anything, it's a constant, so this cancels with this, right?
Okay.
And then you're left with, this is good, because now you have a sine theta, d theta. And then so you just take the integral of that, which is like negative cosine, right? This is an easy one. So the integral of sine theta is negative cosine theta.
That's 1 and -1. Okay.
Yeah. And then after that, you get this. And then, so you're not done yet, which this is pretty fun for this problem. So like now, what was it asking you? It's asking you what is the magnitude
And the direction.
and the direction. So now you have this equation for the electric field. And it's a vector equation. So a vector has like magnitude and direction. So you need to, from this point, you need to plug in a few things, but you don't have all these variables. So you have to like manipulate it so that you do have, you can plug in the givens. So what ends up happening here is like, so they manipulated the R, which is here, L over, because this is the arc length, right? R thing. Yeah. Same thing. The time that we plugged that in was when it's differential form. This is actually the form.
Okay.
And then another thing is we don't have this lambda, so we have it as the charge over the length.
Okay.
We're given the charge, and then you plug those in, and then you get this, and then all the givens, you know, and then you get this guy, and then taking the magnitude, just take the absolute.
Value.
So yeah, so and then even just reading off this guy, you could already tell what the direction is, right? From So yeah, that's pretty much how that works out. I would say this problem can probably change by just know like what concepts are being applied. Like the derivation here isn't that bad.
Okay.
It's just knowing like the integrand and the assumptions here. The arc length, and then what else is there? This lambda or this sine. Maybe they can change this to like, maybe they can rotate this guy.
Yeah.
And then this would be cosine, instead of
Oh,
sine.
it's sine because it's vertical.
Exactly.
Okay.
Yeah. And let me see. And then I think that's pretty much it. Like the ways it could vary. I always tell students like, uh, look at like the most difficult questions on like the chapters, and then not only look because like the professor's not just gonna pick those out, right? Like they're
Yeah.
and then see how else it can be varied, and practice those problems, not the ones specifically, but obviously know the procedures.
Okay.
And yeah, that's how you do that. Um, how's that one?
Pretty good. I was gonna say for the direction, how do you know that it's towards the left because that's the only way it can go, I guess, because that's where
This
the
guy, yeah.
line is.
This
Yep.
guy's here, that's like, and you're gonna have an electric field this way.
Okay.
If it's up, obviously it's gonna be not I, but J. So,
Yeah.
and you assume, I mean, for me, you can always assume whatever, but like positive for me is right, X, and then Y would be positive upwards.
Okay.
And then depending on your assumption, yeah, like it will correct itself in a way.
Okay.
Like it all depends on your assumption. Okay. So let's look at this next one. All right.
Oh,
What do you
yeah.
think about this one?
This one, so I was following, except for, I wrote it down somewhere. Hold on. Get to it real quick.
Okay. This one's a fun one because this is when we finally apply you know, the the Newton's law, and
Yeah.
as well as the next one because I feel like there's always that connection, but a lot it always gets a little lost because in mechanics one or like physics one, it's like oh now you can actually apply it because there's a force. It's the same force that in Newton. So
Oh, okay. I know what my question was. It was, how do I know that the electric field is in the Y direction?
or which one? This one?
For that one, yeah.
Let me look at this. Vertical distance. Probe moves in the horizontal. It enters the uniform time required for the enter that horizontally. The vertical displacement. So this is x. Okay. Oh, this guy EY.
Mhm.
This is a vertical acceleration. It's for B, yeah, especially yeah, because it says vertical displacement.
Okay. Okay. I gotcha.
Yeah, yeah. The wording's very. They really will like inform you,
Yeah.
Yeah. So like, let's try to. Oh yeah. So like, what's not given here? Like before we go over it is are like there's givens for a proton that you know, right?
Yeah.
And then those are like mass and then the charge. So that
Yeah.
for the exam, yeah, I guess know those for constant wise because they're never gonna give those. Like those you
Okay.
have to know. And yeah, and so like if you look over here, this first one, it's asking you the time interval, right?
Yeah.
You're given this velocity. So at first, like it doesn't really make my like you can't really picture out like how am I gonna like solve this, but in essence, like since you're given velocity, and
Mhm.
then like and velocity by definition is just what distance over time.
Yeah.
So if you're given that, you could just use that equation like specifically if you're not given anything else to work with. So
Okay.
like I would just take because you have velocity, you have the d, it
Mhm.
gives you in the question, and then that's like a one stepper. You just had to like think about like what equation that you had to use for that.
Okay.
And like B is like the probably the bulk of it. Like so, the vertical displacement during the time interval in which it travels 5 centimeters horizontally. So
Yeah.
this is when you finally apply this guy, because so like what's the definition of like the electric field? It's just force over charge, right?
Yeah.
Yeah, the force over charge, and you can manipulate that equation so that you can actually get just the force, and by that force, that's the same force in F equals ma, second law.
Okay.
So that's the two equations that you have to think about. Can you like, for that like is that obvious? In essence, when you're thinking about it's like this question, it's vertical displacement during the time. When it's saying vertical displacement, uh, during the time when it travels hard. So when you take a look at this, like I would just say like you do apply that because
Mhm.
you need the acceleration. You need that
Okay.
acceleration in this equation, right? Like
Yeah. Okay.
But this equation itself is something probably like, oh, like why do we apply equation of motion? That's how you get the vertical displacement, right?
Yeah.
And that's like mechanics one, or when, and that's just, this equation is just a very common equation. So you know that there's an AY here. And
It's
that's how
like
you have,
y final, right? Or is that the equation?
yeah.
What's okay, yeah.
There's this initial velocity. It's not as obvious, but this proton is at rest in the beginning, and it just moves because it moves aside.
Okay.
It says like it's already. So it's like one of those things, you know, like maybe because if you don't assume like the initial is zero, I think this equation doesn't turn out correctly. This one,
Probably not.
yeah, but this one is always initial in this case, and then since this is moving, so it's just one of those like, okay, maybe try it. If the answer doesn't make sense, then try it without zero, or try it with for the v. But yeah, like just to go back to it. That's the reason why you have to find the acceleration in the vertical direction.
It's because you have to use that equation. Okay.
Yeah, and then so once you apply that and then manipulate the electric field equation, you apply the givens, then you get this acceleration, and then you know that this is at rest in the beginning, so that cancels out in the vertical displacement equation. And then this simplifies to 1/2 AYT squared, obviously. And then, you know, this question builds on its own, builds up on its own. So you already have this T, right?
Mm-hmm.
And for B, you have this you have this AY.
Mm-hmm.
And in the end, this is pretty much just plugging that in. And then you have the vertical displacement or distance.
Okay.
It's like, there's a lot of steps in it, but you have to think about, the hint there was it is a displacement. So maybe you would think about this equation first.
Okay.
And then like maybe think, okay, this is, you know, all the different parts. And that will lead you to, you know, finding this and eventually this guy.
Okay.
Okay, let's take a look at the last part. Let's see. The horizontal and vertical components of its velocity after it has traveled 5 centimeters horizontally. So, do you remember applying this equation? This is also in equation of physics 1. So, let's just take a look at that. So it says the horizontal and vertical components of velocity. So you have that's Vy.
Okay, yeah.
And Vx, where did this one is given to you, right?
Yep.
Vx is given to you. So that's good. So Vy is the only one that you need to find. So I think you have all the info, right? For that. You just need to think about like, is this the right equation to apply?
Okay.
And then I think it's not as bad because then you already know, because it's asking you for horizontal and vertical. They give you like the horizontal, and then, you know, since you thought about using this equation, right, for B, for the displacement, I guess the next step is, what is the velocity at the final velocity? So
what would the initial velocity in the y direction be 0 as well?
Yeah, this one is 0 because we're only given this guy, right, in horizontal.
Yep. Okay.
Yeah. So, you know, this one goes to 0, and then it pretty much falls into this equation, and you already have these two variables, AY and BY. And then you get that. And then in the end, you just have to apply. I thought at first you had to take the net, but I think it just wants you to do this. Because then like it asks you for the component, right? The component.
Oh, yeah. And so how did we end up finding Vy?
So Vy is because it's asking for a horizontal and vertical component velocity. So you're given horizontal, right?
Yep.
But then you don't know your vertical velocity.
Okay, and so you just plug stuff in.
Yeah, but then like you know this equation though, right? Like
yeah, yeah.
Because it's pretty much all the equation of motion, like displacement, velocity, and then, you know, it's not moving in the y direction.
Yeah.
So this is at rest in the y direction. So and then you just, you know, simplify and plug in the values that you know.
Okay.
And then yeah, that's it's not bad, but it's really like taking back what you learned in like physics one and applying
Yeah.
it to electricity now.
Yeah. There's a lot of that.
Yeah. What do you think of this? If you were to like, there's a lot like this is a common problem when maybe like how I would approach this is like maybe change this guy or maybe not given like a horizontal but given like a vertical. Uh,
Yes, you just solve for the other.
yeah, and then change B to like what is the horizontal displacement? Okay. You know,
Okay.
the more you really understand like the how the problem, how the givens affect like the solution,
Mhm.
and then like kind of like manufacture your own. And because in the exam it's kind of like that. Like the professor's gonna think of that as well, right? He's gonna think of
Yeah.
like how I can like make this different, but not too hard for them.
Okay.
But this one, there's actually there is no calculus. It's just knowing the equations.
Equations, yeah.
Yeah, which one to apply.
Okay.
All right, so let's take a look at this one. Okay, so this is actually my favorite one. What did you think of this one?
Um, I know I knew how to do it. I just don't exactly know how it applies with all the charges and everything.
Yeah, I know what you mean. It always goes back to like that Coulomb, or it's either Coulomb's equation or the electric field equation, because both of those have forces, right? It has F in
Yeah.
it. Like so, you could either one apply those two as long it depends on what's given to. For this, I'm thinking it's probably this guy, yeah. So this is the electric field equation
Okay.
manipulated.
Yeah.
Yeah, because it doesn't give you like point charges, so you can throw away coulombs and just apply electric field. But that's how I
Okay.
usually think about this, because knowing all that theory and then like okay, the givens give me this, okay, I'll throw away the other guy. So let's take a look at this. So when you're given like something like this every single time, a sliding block, you're always going to be thinking free body diagram, right?
Yep.
Yeah, and then that you probably done a lot of it, but like let's take a look at how it's applied to like electricity. So that's nice to actually drew this out. And let me
Yeah.
just, but like let's try to like break it apart. So you know how it says here like the electric field is on like down inclined, right?
Yeah.
You can assume this going this way or this way. The only thing is the final answer, depending on like it's pretty much the same thing, right? Depending on your final answer, if it's negative, then what you assume is like the opposite
Okay.
direction. Uh, and I think that's like the most important thing because you already know there's a gravity force, right?
Yeah.
Going
Your MG. Yeah.
mg, and then this part you know how they got this direction, the fg.
No, I'm not quite following that.
Okay. So we know like yeah, the incline always like throws people off, but when you point things down, right, for like the weight, you always have like this theta, right?
Yeah.
Like, and then if you take a look at this one is going down here because you're gonna have to draw this. You're given this theta, and
Yeah.
then you have this pointing down, and then but this has to be perpendicular.
Okay.
So you have this like theta, but by like I think it's like complementary angles. Since this is theta, this also has to be theta.
Has to be theta, yeah.
Does that make sense?
Yeah.
Okay. So with that, since that, because I'm trying to explain like not only the FG but what it's going to be. So with that theta, you also draw a line here. You also draw a line right here, perpendicular to this force, and then this theta is going to be this guy, right?
Yeah.
And then so now this is going to be sine. So
Okay.
it's gonna be like mg sine because it's the opposite.
Okay. MG sine theta. Okay. Yeah.
And then what about this guy? This direction
That's the direction of the
of this
electric
force of this force.
of the force. Okay. Yeah. Okay.
And then like this is because you assume that this way there's gonna be like a reaction force.
Okay.
If you assume that this way it'll be going. It's a force as well. It's a resisting force of this electric field.
Okay.
So it's always going to be opposite of what you assume the direction of your electric field is.
Okay.
Yeah, but like I said, you can either assume the electric field going upwards. That means then your FE is downwards, or this way, which is like going upwards for the FE.
Okay.
And
So
let's
just
just
as long as they're opposite.
yeah, because it's a resisting force.
Okay.
And then so first, let's get the FE. Like knowing that it will just be the charge times the electric field by
Okay.
definition. That's your FE. And then you're given the mass of the block. Yeah,
Yep.
you get the mass of your block. So let's see. The mass of your block, and then like you're also given the charge, so negative Coulomb.
Yeah.
So that's fine. And then you're also given your incline, which is they have to give you that one. And
Yep.
then gravity is always constant. Gravity are constant at this value. Oh yeah, how does your professor work with like does he usually like giving you guys like for homework SI units? Does he ever give for physics usually it's like SI, but does he ever give it to you in US units?
No, I had some of that in physics 1, but I haven't had any of that in physics 2.
Okay. Okay, I mean I'm just thinking he's gonna stick to like all the SI.
I think so, yeah.
Yeah, it's quite brutal. Like if it's like fluids, sometimes it could be given in either one. But I
Yeah.
think yeah, for electricity, I think we'll stick to SI. But I guess like be ready, for converting anything.
Yeah.
Okay, so like I said, like this gravity force is gonna be mg sine.
Okay.
And then Fe is Q times E. And so the first thing here is you need the magnitude of the electric field. Is that what it's asking you? Find the expression of the magnitude of the electric field. Okay.
Sorry. Okay, sorry.
No, it's all good. Okay. All right, so
Hello?
yeah, can you hear me?
Yep, I can hear you now.
Okay, good. Yeah, and like a lot of my classes always have pets too. So they get excited when they hear.
Hear things, yeah. Mm-hmm.
Okay, so after applying the gravity force, the electric field force, and you always have to apply and think. This is kind of similar, right? It's the equilibrium condition.
Equilibrium, yeah.
They're gonna be equal in the x direction. Oh yeah, I gotta explain. So you could always assume like where is your direction of x anywhere. Like you could make it assume here. You could make it assume here. But like this is a block, right? And then you need like these guys. They're given these guys. Why don't we just assume the x direction going this
that way?
So you can assume it going downward as positive. It doesn't matter, but as long as it's along the incline. So that's what I would do, and then you make them equal because they're opposite directions.
Yep.
And then so you just plug them in, and then the reason, at first the reason why they're doing this, you don't have to, because it's magnitude. You could do this later on. You don't have to do this now.
Okay.
Just plug it in, and then like take the absolute later on. So after that, they just plug in the values, and voila. And then here. I was trying to like read some of this like now the reason why they're telling you guys this is it just depends on like your assumptions,
Yeah.
Like, direction of the electric field down the incline. You know that when this is like positive, this is what you assume.
Yeah.
And if you assume going up, then it's gonna be the other way. You're gonna have to it's gonna be a negative number pretty much. And yeah, what do you think of that one?
Well, it's not too bad. It's just I just needed a refresher, I think, more than anything.
Yeah, it's I would say this is like one of those problems that would probably show up because it's like pulling everything, like for electric field and forces.
Yeah, that's kind of what I figured.
Yeah, and they could probably like just thinking how this can change is maybe the inclined one always makes it more difficult. Maybe if there's like a friction force, If there's a friction force, you know how to do that one?
Yeah, I do. I believe you just add the friction force in, and
Yeah.
it's working against whatever's moving up or whatever.
And if someone is like pushing it, if someone were to like hold on to this block, they can also
Mhm.
ask you, what is the, I guess the like the charge for it to be at rest, something like that.
Okay.
Yeah, they could ask you like, what is the electric field to keep this at rest? And they could get very creative with these, like either the Q or the E. And obviously, if it's at rest, then it has to be zero. You're given all these other forces acting on this block, and
Hmm.
then one of these, and then you can find one and not the, and then given the other.
You can put force. Yeah.
Yeah, that was fun. Like, I don't know. Do you have other ones?
Let's see. There was one more I was looking at. It was 63.
Let me take a look at it. Oh, okay. So this is an integral one.
Yep.
Okay, let's take a look at this. Okay, determine the electric field. So, let me think. K, so the electric field K times Q. I'm guessing this is Q. And then it's just in terms of a line. It's a line of charge. So,
Okay.
oh yeah, it tells you that the linear charge density is this guy. Okay. So yeah, since it already tells you that it's a linear charge density, you could just make, instead of KQ over X squared, it's just K lambda over X squared, which, which
Okay.
is this, which is like the typical equation if it's a line, right? Line chart, you have this lambda. And then you just plug in, you know, lambda naught and X naught. Let's see,
No. So you're getting the lambda from the Q equation?
yeah, it's the same as lambda L. The lambda Q is lambda L, right?
Okay.
If it's a line of charge or like a line, Q is always lambda L, and then the L here is delta X.
Okay. Gotcha.
Yeah, they skipped that part. Like they took the differential of E. They skipped that part. It's clear that way when you take a differential of E and then equals K times Q over X squared, and then when you take the integral, then the left hand side is E, and then you take the integral on the right hand side, and then the only differential here is like the L, the length, dx,
Okay.
and then like the constants are, when you plug in this lambda because it's giving you the equation. I think that these not ones like are the constant ones.
Okay.
So when you plug this in, the lambda naughts and x naughts they come out, but there's an x here, right?
Yeah. So it's gonna
So
be
this x just gets applied to this like integrand that's already in here, the x
okay.
squared.
Yeah. So x cubed is what it becomes.
Does it tell you what this direction is? X tends to positive infinity.
It says positive infinity.
So x naught to positive infinity tells that's the limits.
Okay, the bounds. Yeah.
But this right here, how do you know it's like on the left?
I have no idea.
Um, Line of charge starts this and extends to it's going to determine the electron at the origin. Why did they assume it as negative? X determine the electron at the origin. Yeah, there's like, because at least the other one it shows you a picture of where the
Yeah,
where's
where everything is.
the what if you assume that you could just assume this is positive?
Yeah.
Uh, yeah, it seems like that's something that I would probably like. Oh, why is that? Linear charge, the electric field. Let's take a look at another one if there's something similar. Literally the origin due to a line charge that extends. Maybe it's just an assumption. A lot of these I've seen. I can come back and like tell you about it. Maybe it's just an assumption that they always assume it as like negative x.
Okay. Huh.
as of now.
Yeah.
Yeah. I'll tell you like if I find out something different, but it seems like that's what it is.
Okay.
I think the probably the hardest part, I mean, is just like knowing, the setup of the integrand here.
Yeah.
Because what if you were given this? You already know that Q is lambda L, and
Yeah.
then would you be able to set up just this part if you weren't given this part? Yeah.
I think so. Yeah.
Okay.
And I think that's just going to take some practice too and some memorizing.
Okay. Yeah, because like E is just what K times the charge
Q
divided by
over
x squared,
MC
right?
squared.
Yeah. Or like D squared, whatever. Um, but this lambda, once you make it into an integral, the differential is always the length.
Okay.
Because lambda times the length, so it's always going to be the length. Never.
Okay.
That's like some. I say, okay, if I see that again, that's always going to be the case.
Okay. I
And
mean, that
like,
makes sense. It's DX.
yeah, it's just like this negative. It seems like because the charge is probably because this is going to like positive infinity. Still, like if it, but then is it a positive? The line of charge starts at positive. Because usually when it's a positive charge, it points outward, and if it's a
Yeah.
negative charge, it points inward, right? So it's but nowhere in this problem it tells you it's a negative charge. Does it?
Negative charge. Yeah.
It doesn't tell you it's a negative charge.
That's weird.
Yeah, yeah, something lacking, but whatever. I guess the concept is still,
The same.
as
Yeah.
long as you apply this, if you miss this negative,
It'll be a
like,
few points off, but
how's the exam gonna be? Is it like are they gonna monitor you while you're taking it?
yeah, they are. Which is kind of annoying, but it's yeah, so it's going to be just myself and a pen or pencil, and they'll give us a formula sheet, which I was
Okay,
looking at it, and it's kind of helpful, except it doesn't label anything, which I mean, I guess makes sense just so that you know it. And
okay.
then it's going to be like 7 questions. I think it's like 4 from chapter 23, and then
Oh, four
3
from here. Okay, that's
from,
good. Okay,
yeah.
that's already more than half. Okay, that's good.
So it shouldn't be too bad, but it depends entirely on the problems that he chooses,
Yeah.
um, and how fast I can work because we're only given an hour and a half.
Okay. Wow. There's a lot of problems for that long.
I know. Yeah,
What
and
you
I
could do, just do like, did you already start doing most of like chapter 23? Like just start doing
yeah,
the problem.
I'm basically all the way through chapter 23.
Oh, awesome. Yeah, like a lot of the students, the reason why they, not do so well is they just do the homework problems.
Hmm.
And
Yeah,
then for me, like the way it's a lot of work, obviously, right? That you do all the problems, but
yeah,
what you can get from that is intuition.
yeah,
Like different scenarios of like how a question can be asked, and then givens can be like given. Then like you get to know like okay, what are the different steps? Like I can mess around with like the the conceptual equations because like they're not they're pretty easy equations, but there's like certain ways that they can be asked, and then
yeah,
like having like a set procedure. Maybe like that's what I've done too. Like in the cheat sheet is not only write the equation, but write like step 1 for this type of problem.
yeah. The issue is I don't think we're supposed to write anything on it. I wish we could. It's kind of silly that we can't. Uh,
Okay. So it's just equations. It's just
yes, it's just equations, as far as I'm aware, and I think that's just the way he likes to do it.
okay.
Uh,
That's
but yeah,
fine.
no, because I've done what you're talking about before, and it's usually very helpful.
Yeah, because it's just like that. It could be done that way too, like what your professor wants. That it's just gonna take a lot of like memorizing.
Yeah. No, I really hate that too, because it's like, are you testing our memory or are you testing our ability to solve the questions? But it's his class, his rules. So
But I'm pretty sure, yeah, like going over this, most of it is because like all the other stuff you get already, right? These are just the ones that like, okay, um, you need like a little bit of explanation on.
yeah,
Yeah, I feel like yeah, if there's more, maybe like chapter 23, just let me know. I can definitely like not only this, but maybe work it out and give you like my solution.
Okay. Yeah.
Yeah, yeah, just reach out to me on my Excel, and then like for the chapter 24, did you want to go over that next time?
So I haven't had a chance to really do that. I was wondering if we could do that next week because I think I'll spend most of Friday doing those homework problems.
23?
Yeah, for 24.
Oh, you're gonna do the 24. Okay. Yeah, next week is fine. For the next one, you want to do it next week?
Sure. Yeah, that works.
Okay. Yeah, because I'm super booked for like the next couple of days. What day next week? Maybe for now, just let me know. Like towards like this weekend.
Yeah.
You don't have to like let me know right now, but because I'll
I
just
think
book it. We'll figure it out.
okay, that works.
Okay. Yeah. Just let me know which problems ahead of time. I think it'll be helpful if I can work it out this weekend.
Okay. And so you'll
Perfect.
send me your solutions.
Did you want the solutions for these, like my set of solutions?
Um, I think maybe for let's see, maybe for the integral problems.
The integral problems. Okay. I'll. You know what I can do? I can take a look at like throughout all these like questions, and then pick out a few of those, and then just like do them like using my solution.
Okay. And then the other thing is the point charges where they're not on the origin.
Okay. I'll actually I'll write that down. So point yeah, because that one yeah definitely like that might be a very challenging one, and then the integral
Yeah.
questions for chapter 23. Perfect. That sounds good. Yeah, very nice to meet you. I'll do my best to definitely give you like an A in the exam. That's always
Ultimately,
my goal.
it's up to me. It's my studying. But yeah, no, I really appreciate the help.
Yeah, thank you so much. And then yeah, I'll just I know what was it like I spoke to I think Jill, and then she mentioned so you want to just continue doing the Zoom like from now on?
Yeah, yeah. I mean, that works for me. In the future, if you would be willing to work some stuff out on the whiteboard, that might help too. Um,
Yeah, that would help me out if I knew them, I had like maybe like 3 days.
yeah. No, I'll go ahead tonight or tomorrow. I'll go ahead and go through the different problems and if I don't know how to do it, just looking at it, that's usually my biggest pride is if I can look at it and I look at it and I don't know what I'm doing,
Yeah.
then it's a concern.
Yes. Yeah. Make sure. Yeah. Like for those, that's why I always do like all the problems, and then like okay, circle the ones. Okay. Oh, this seems very off. I don't know what's going on. Yeah. Like pick those out, and then on top of like what I'm gonna give you like the solutions of, just I'll add that to the list, and then give you like my solutions and explanation why the way they did it.
Okay, yeah, no, that sounds good.
Yeah, same with not only for this chapter but 24. If it'd be great if I could do that this weekend, and then like I'll just show you like how I would do it like for us next session.
Okay, yeah, no, that totally works. That's basically I think what I'm after.
Yeah, yeah. Usually like this, the reason why I'm showing it is I mean, like what the next one you'll definitely see it because then it's exactly how you would write it down. Like I would give you what you would write down on the
Okay.
exam, not like this because like, you know how like professors sometimes when they show like a PowerPoint versus like when they write it on the board or like a
Yeah.
blackboard, like it 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 comes out like yeah the understanding of the student is like more like it's like easier to understand if they write it and then they give you their assumptions rather than like okay this and it's not as good, right?
Yeah, no, I totally agree. I mean, I think Jake's a good resource, but yeah, it doesn't have that just writing it down kind of thing.
Yeah. Okay. Cool. Hi Jennifer. Yeah. Very nice to meet you.
You too. Thanks.
Have a good one.
You too.
Yeah.